Publicly, modern science treats the moon as a geologically dead rock. Privately, suppressed data sets point to a surface that is highly active and remains unexplained. The center of this contradiction is the Aristarchus crater. It sits on the lunar near side, standing out as the brightest and most geologically complex feature we can observe. The official explanation for its intense brightness is entirely geological. Scientists attribute the high albedo, the amount of light it reflects, to relatively young meteor impacts exposing unweathered, silicate-rich minerals. However, that standard model struggles to account for a persistent anomaly. Aristarchus has long been ground zero for transient lunar phenomena, sudden flashes of light and hazes that defy normal geological behavior. Detailed reports of those flashes were locked away for 50 years. They sat buried in classified military files until a recent unannounced declassification event brought them to light. While the public scientific consensus focused on natural processes, military intelligence was conducting a parallel investigation into lunar anomalies that standard textbooks cannot explain. The recently unsealed Department of Defense files reveal that the 1972 Apollo missions documented severe, unidentified anomalous phenomena during their orbits. During Apollo 12, astronaut Alan Bean radioed Mission Control to report rapid flashes of light. He described the objects as escaping the moon and accelerating away from the surface into the stars. In 1972, Apollo 17 lunar module pilot Harrison Schmitt reported 3 luminous dots holding a rigid triangular formation near the horizon. He described the particles as looking like a 4th of July display. These encounters were verified by human observation and tracked by military sensors in real time, which helps rule out camera glitches or simple lens artifacts. These records suggest that the Apollo missions were more than a collection effort for geological samples. They marked our first sustained tracking of geometric UAPs in deep space. Decades after Apollo, modern orbital probes began scanning the surface with far greater precision, using the Moon Mineralogy Mapper and the Diviner Lunar Radiometer. This visualization shows the M3 spectral parameters. Scientists use these graphs to map specific mineral compositions by measuring thermal emissions. The graph shows a significant deviation in the southeast ejecta, capturing signatures inconsistent with surrounding basaltic materials typically found here. Researchers applying resolution-enhancing algorithms to the crater floor discovered unusually reflective, linear surface features stretching for kilometers across the basin. These structures feature exact orthogonal, or 90-degree, intersections and stratified layering. These specific geometric patterns are not typical results of impact fracturing or regolith deposition. The reflectivity of these lines is remarkably high. The albedo readings suggest a density of artificial glass-like materials rather than the dull minerals of the lunar surface. The presence of precise geometry and glass-like albedo readings in the raw telemetry creates a significant conflict with existing models of lunar formation. Current military tracking networks now include space domain awareness stations that specifically monitor the moon for artificial changes on its surface. Their primary tool is the thermal quartz crystal microbalance. These sensors detect microscopic dust fallout or gas by measuring minute changes in the frequency of a quartz crystal. The sensitivity of these instruments is high enough to detect less than a single layer of dust kicked up by activities thousands of kilometers away. This surveillance network allows for the tracking of physical and geometric changes in Aristarchus with extreme precision, monitoring for any activity that might explain the anomalies. We are left with 2 distinct data sets. In the 1970s, Apollo astronauts documented dynamic, triangulated light formations that appeared to accelerate away from the moon. Today, orbital scans reveal static, geometric structures and artificial albedo readings concentrated in the Aristarchus crater. Conventional theories involving rocket debris or unweathered craters have difficulty explaining both the rigid movement seen by astronauts and the orthogonal geometry seen by probes. After the Apollo missions documented these events, 50 years passed with no human presence on the surface, even as the list of unexplained observations grew in classified archives. As humanity prepares for a heavily funded return to the lunar South Pole, our mission parameters have expanded. We are going back to the moon with the sensors and mobility required to finally identify the source of these anomalies.